In this video, I'm going to work some of the application problems that you'll see in the test. So here, you had some of these on the study guide, but we're told that the force of gravity varies, that's the clue to put the equal sign, directly with its mass, so that means that mass goes on top, and inversely with the square of the distance. So that means, you're going to do the distance squared on the bottom. And there's going to be some coefficient. You could put it like this, in case you're curious, like we always put K on top. If you want, you could also write the force is equal to K, and you could do M over D squared. You could do it like that as well. It just looks a little bit nicer to put it this way. But this is what you're expected to be able to construct. Very similar like we had before, except we're using actual units instead of just X, Y, and Z. For our number, this is from section 8.3. It's dealing with weighted averages. So if you earn an 82% on your first test, okay, so you get on your first, you only had one test where you made an 82. We want to know how many consecutive tests do you have to get 100 on to bring your average score up to 95. Now I'm going to work this two ways. One way, I'm going to do it just a guess and check way. So you can do 82 plus, you can assume you made 100%, and instead of writing 0.82, let me just write 82 instead of using decimals. And I take that and divide by 2. All right, if that works out, great, I'm done. If it doesn't work out, I would end up adding another 100, and then instead of dividing by 2, I divide by 3. And if that doesn't work out, I add another 100, and instead of dividing by 3, I divide by 4. You can see how. So you can see this will get me the right answer. And again, the goal is to get up to a 95. But getting there, I'll have to just repeatedly do this calculation over and over, but just adding more hundreds each time, and then also increasing my denominator because the idea is I've done more tests each time. So there we go there. After 3 tests or 2 100s, it hasn't been enough. So I can do one more 100. And that will probably get me enough to get me up to a 95. Make sure I'm dividing by the appropriate denominator. So it would take me 4 tests to get at least a 95%. Now, another way of doing this, and we're going to work a similar example in a second. There was only 182, but the idea is, well, how many hundreds are there? Instead of doing like 100 3 times, let me say I don't know how many hundreds there are. I'm going to do 100 times x. And I'm dividing by, well, there's only 182 plus x represents the number of hundreds I made. And so you could set that equal to 95. If you solve this equation, you would also get the same answer. But with these application problems, if guess and check works for you, it's definitely a legitimate strategy, especially if you're dealing with multiple choice tests. It's a great way to do it. Now, one thing I'll caution you on is that if I try to solve this by, cross multiplying or whatever, and then distributing and solving for x, if I do it by actually solving that, I get 2.6. Now this happens to round up to 3, but even if it didn't, let's say if it was 2.4, I would still have to round up to 3 to get at least a 95%. So it would take you at least 3 tests to do it. But either way, you should say that it would take 3 tests, assuming you made 100% on each test to bring the average up. Now we're going to skip around a little bit and work a problem from 8.6, but the reason is because it's very similar to the last one. So you have 4 tests and you made an 84%, so there's 4 tests that are each worth a score of 84. And then you think you can score some 96s on every other test, but you don't know how many of those you would need to do to bring your average up to 90. So you want your desired average to be 90. Well, then what do we divide by? Well, the 4 tests are locked in, plus we don't know how many 96s we're to do, but the idea is just to make this consistent, we're doing 80, score of 84 times how many 84s we got. So that's where this comes from. And then a score of 96, I don't really need the parentheses, I don't like the way they look, times how many 96s you got. And if you solve this equation, when you solve this, you actually get x equals 4. It takes 4 tests. And the reason is because these are both 6 percentage points away from 90. So let's say we switched it up a bit, okay? We worked this one in class. Let's say instead of scoring a 96%, let's make it interesting. Let's say you could only make a 92%. You're only confident you can make a 92% on each test. So instead of having a 96 here, let me put 92, but everything else will still be the same. So how many consecutive 92s will you need to bring your average up to a 90 overall? Well, again, you could guess and check by taking 484s plus a string of 92s and take the total things you're dividing by and keep guessing and checking and adding 92s, but that's a really slow way of doing this. Instead, I could solve this rational equation. I could enter this expression in here, okay? That's what I have here. And I can keep just substituting different values of x until I get the 90 average that I want. So I can go, the best way to do that, I find, is to go into, and I'm going to set my table value to be able to edit it as I want. And so let's say I did it for, if I did 0 tests, well, the average, to make sure this is working, the average should start off at 84, and that makes sense because I only have 84s. If I got 1 test where I made a 92, the average would come up slightly, but it's outputting decimals. I don't like that. If your calculator is doing that and you want it to output decimals and not improper fractions, you can force that by changing this here from auto to decimal. So I'm going to do that. And so now if I do 1, the average is up slightly, but it's not great. 2, 3, 4. It would take me a lot of 92s to bring this up. So let me try 10. And it's like, oh, even 10 is not enough. 11, 12, and there we go. It would take me 12 92s to bring that up. Which makes sense because 92 is weaker, so it would take a lot more of those to compensate. Let's do one more scenario. Let's say instead of a 92, let's say we're a 94. Well, it took 4 96s to bring it up. And so let's see how many 94s it would take if I put 94 instead. Let me try 4. No, not quite there. 5, 6, and it would take 6 94s to bring that up. So you could, knowing how to do this model allows you to substitute a lot of different values to figure it out. For another example of this sort of a weighted average type scenario, so if you look, this is from section 8.5. It's number 30 in the textbook, but it works very similar to that one that you had with the grade. So say this is you have 2 different gas mileages you get in your car. If you drive half and half on each of them, and you want to find your overall miles per gallon, well, that's going to be really easy. It's just going to be the average of these two. But instead of assuming that'll be the average, the idea is this. You drive half going 25 miles per gallon, and then you drive the other half of the time going 30 miles per gallon. So if we take this sort of weighted average of these two things, another way of seeing this, if I'm multiplying each thing by 0.5, that's the same thing as taking both of them and multiplying by 1/2, which is the same thing as taking both things, adding them together, and dividing by 2. So if you want to see this as, the 1/2 right here, I can kind of see that as the 1/2 being factored out, and then the 25 plus 30 there. But that makes sense intuitively that if you're going half and half, that the average would be right in between, which I believe comes out to 27.5 miles per gallon. Now that's really easy, but it's not as useful because it's not as likely that you're going to be driving half and half on the highway as you are in the city. So let's look at a different weighted average. What if you do 60% of your driving on the highway, which if you do 60% of your driving on the highway, you're going to be getting 30 miles per gallon. And then you're going to be doing 40% of your driving in town or in the city. So that's going to be times 25 miles per gallon. And then this will give you the weighted average there. Before we calculate it, think about it. Which one would it be closer to? Would it be closer to, again, the 60%, the highway mileage is what's associated with the 60%, and the 25 is what's associated with the 40%. So toward, um, if it's weighted heavier toward the highway, you'd expect it to be slightly higher than 0.75. So I'm expecting it to be maybe 28, maybe 28 and a half or something. And of course, it's higher than the average, 28. So this is just really similar to that one with the grades, but it's just another example of what situation you can use these kind of rational functions. Next, we're going to work some from 8.6. So we're going to start with something really easy. So if an airplane is going 350 miles per hour, we worked this in one in class, but a tailwind of 40 miles per hour is what's helping it out. So how much would the plane be going if that tailwind were not helping it out, meaning if it were in still air? So that's very simple. It's just if you took away the wind, it's not helping them, you lose 40 miles per hour speed, so it'd be 310 miles per hour. Now we're going to build on that the next. Here's one where we put that more to use, and we worked this one in class, but this is just a review. We want to see how long it takes for the plane to fly 700 miles if it's going 360 miles per hour. And the idea is since you have your speed is equal to distance over time, you have your speed is going to be 360. That's equal to the distance, which is 700 over the time. We want to solve for that time. So you solve for time by taking the 700 and divide it by 360. You could work it out longer, but if you just swap these, it works out nicely. And the units work out too. So the time it takes is right about 1.94 repeating hours. Now, as much as I like decimals, it's really makes more sense. Say it takes about like sorry, I put the repeating bar over the wrong thing. It makes more sense to say it takes about 2 hours or really close to 1.95 hours. Honestly, even though I know it's or 1.94 hours if you round properly. But the improper fraction, since we're using this as an intermediary step, it's a good idea to just keep this as an improper fraction. If you don't, if you use it this way, it's not going to throw the answer off that much. But when we want to calculate B, the return trip, there's a tailwind that helps it. So the speed's not going to be 360 miles per hour anymore. But the thing is, we don't know the speed of that tailwind. So, but what we do know is that the round trip, and be very careful, it says round trip is 3.5 hours. Well, to figure how long the time, I'm going to call this the time of the return trip. It's going to be the total time. It's going to be the time of the round trip minus the time of the going there trip, which is 1.94 repeating. But this is too hard for me to enter into my calculator. Instead of entering in 1.94 repeating, it's a lot more convenient for me to enter in this improper fraction. And so I get 1.5 repeating. So now that I have the time, I can find the total speed by taking the distance, which is still 700 miles, because the distance there is the same as the distance back, dividing by 1.5 repeating. But again, that's too hard to enter in my calculator. But instead of using the improper fraction here, I'm just do divided by, walk up, grab this number. So I get this speed right here, which is, if I would have used the improper fraction, it would have actually came out to exactly 450. Because even the calculator is as exact as it is, it's sort of rounding here. But this is the total speed. That's not the speed of the tailwind. It's the speed of the plane with the help of the tailwind. And since I know that the speed by itself can go, let's see, how fast did it go without wind? 360 miles per hour. So that means the tailwind speed is going to be about 90. But these are the kind of problems that I'm going to want you to be able to figure out. It's, work being done or distance, a speed being done, uh, those kind of problems. So the tailwind, oops, let me not call that T for time. Let me call that the speed. They said X for tailwind, so the speed of the tailwind is 90 miles per hour. Let's work one more. That's really the most important one. So this is that combined rates problem. So one pump, we did this in class. One pump can do the work in 4 hours, so it does a fourth of the work in 1 hour. Plus, this other pump can do the work in 3 hours. That means it fills 1/3 of the tank in 3 hours. And then we want to know how long they can fill it together. This one represents the whole tank being full right there. So this is the full tank, or this is the work, the job being fully complete, 100% complete. And then you just solve this using either rational equations, or you can solve it in another way. But let's solve it using rational equations first. We want common denominators. This is 3/12 t plus that's 4/12 t is equal to, let me just set this equal to 12/12 because why not? And then I can just multiply 12 by everything. And since I do it to both sides of the equation, it works out. So I get 7t is equal to 12, and so t is equal to 12 over 7, or it's 12 over 7 hours. That's fine to leave it as an improper fraction, but it makes more sense to write it as a mixed number. So 1 and 5/7 of an hour. Now, if you leave it as an improper fraction, you get to see the connection of a formula we get to use. A times b over a plus b. If you notice, 4 times 3 is 12, 4 plus 3 is 7. This is the shortcut to do these. You are more than welcome to use this shortcut. I'm not going to give this to you, but you're welcome to memorize it. If you don't, the reason why I'm normally all about giving you formulas. But this is something that is really, really, really worth memorizing because you're usually going to see at least one of these problems on, an ACT or SAT test. So I'd really highly encourage you to memorize it to solve these problems. And it's always dealing with these work problems. How long can they do a job? Let's work one more that's actually similar. Again, this is one that we worked in class, so it shouldn't be your first time seeing this. But you can do a job stuffing these envelopes in 4.5 hours. Or I sorry, together you and a friend can do it in 4.5 hours. You do it twice as fast as they do. So the idea is you don't know either of the times that it takes you. So here's a couple ways to look at it. Here's one way we tackled it in class. So you do the job in this many hours, and your friend does the job in twice as much time. So if you compare how long it takes you, it's like an X and a 2X scenario. Or you can see it this way. So altogether, there's kind of 3 units of time that you can split this up into. So if you were going to split up the work being done, since you take half as much time as your friend takes, what you should do is take that 6750, you can split it up into 3 parts, which is, if you split it up in 3, you get 2250. So you twice as many envelopes as your friend takes, and they would take the rest. So you have twice as much as them because if you spread it up this way, you'll both be done in the same amount of time. You don't want to split it in half because you would finish your half before your friend finished their half. So you can use this to get individual rates. Well, you guys do it in 4.5 hours together, but in that 4.5 hours, you are doing 4,500 of those envelopes, and they are stuffing 22,250 of those envelopes. So you're doing, if you divide this, 100 envelopes per hour. They're doing half of that. If you divide this, you should get 50 envelopes per hour. And now, since you have your individual rates, you can see how long it would take you to do this alone. So since you do 6750 envelopes, if you can only do 100 per hour, take 6750, and that's envelopes. If you divide that by 100 envelopes per hour, what happens is the envelopes cancel out, and since this is the denominator of a denominator, this comes out on top. So you get 6.75 hours is how long it takes you to do it alone. And your friend should take twice as long because they're half as fast as you are. So your friend takes 13 hours to do it by themselves. This is just one way to tackle this, but we can also confirm this using that formula. If you do A times B over A plus B, where A and B are your individual rates, if you take 6.75 and multiply it by 13 divided by 6.75 plus 13, you sure enough will get 4.5 hours, which is the time it takes you to do it together. So there's many ways you can tackle it just as just one thing, but these kind of problems, the most important one being 37, are ones that you should absolutely use. You can do rational functions, which is what we've been building up to. We've been building this up to this whole chapter to work these kinds of problems, just to show that really this formula does work. Instead of just memorizing a formula and working these. We can do it the rational function way, but you can also do it using that shortcut. That's it for the application problems.